Hello, everybody. My name is Matan. I'm going to present our work called Splitting the Difference on Adversarial Training. I will give a very brief background for those of you who doesn't know adversarial examples and adversarial training in general, and then we will jump to the topic of this talk. So, as a general background, adversarial examples are generally crafted by adding small adversarial perturbation to the inputs. These adversarial perturbations are found by optimizing the input to maximize the prediction error. Deep learning was shown to be extremely vulnerable to such adversarial perturbations. And adversarial training in general is one of the most effective ways today to enhance the model's robustness against adversarial attacks. And the basic idea is to train the model with adversarial examples alongside to the original data. And usually when adversarial training happens, the adversarial examples are assigned to the same label as the original class. For example, if you have an adversarial cat, it will get the label of a cat, and so on. So what's the problem? The problem is the natural robust accuracy trade-off. Tsipras et al. Usually previously argued that the robustness may be attached with the natural accuracy, and usually the trade-off is inherent. Or in other words, that when you try to learn a robust model, the model will lose parts of its original accuracy. And this is not very good for real-time and commercial usage. So our research question was, in adversarial training, how can you avoid significant natural accuracy degradation while still achieving significant robustness? Or in other words, how can you build a robust model that will be consumed in real-world applications where the degradation in natural accuracy is not permitted? For example, autonomous vehicles, healthcare, and so on. Okay, so a bit of motivation. So we argue that Tsipras et al. Are correct, but usually the trade-off happens when the adversarial examples are assigned to the same class as the natural ones. But what will happen if we completely separate the adversarial and original classes? We argue that by separating the adversarial classes or the adversarial examples from their source and generating new parallel adversarial classes, we may be able to maintain the natural accuracy while still gaining a significant robustness. Meaning that our goal in general is to keep the natural accuracy as high as possible while still gaining a significant level of robustness. So our method is called DBAT, double boundary adversarial training. We have a very high level illustration. In figure A, you can think of a linear separator with two classes, the stars and the squares. And then in figure B, you have a very basic adversarial attack that swipes a few of the examples to the other side and basically change the label. In figure C is what the standard adversarial training will do. It will try to generate or to learn a shared boundary for the two classes. But this shared boundary is complex, and what we offer in DBAT is in figure D. We double the number of classes. For each class, we have an adversarial class, but the decision boundaries become much more simpler and smoother. This is the general idea. It also means that if this will work, then we will be managed to keep the original accuracy without almost any degradation. Okay, so the idea, very basic, okay? Imagine that you have a set of n example S with C classes, Y from 0 to C minus 1, and now you define a new class space, which is twice the size of C. Now, during the adversarial training process, which is iterative, right, you return on the process for several epochs. So for each class, you learn an additional class dynamically during the training process, meaning that for each natural example, xi and yi, you generate an adversarial example, xi tag, and you give it a label of yi plus c, meaning, for example, if you have an adversarial dog, if you have a dog image, then you give it the adversarial dog label. If you have a cat image, you give it the adversarial cat label, and so on, using targeted PGD. Why targeted PGD and not untargeted PGD, which is usually used in adversarial training? Because remember that we try to learn completely new classes, completely new adversarial classes, completely new manifold, which means that we need diversity in the class space to generalize. So targeted PGD will not look on specific or small regions in the manifold like untargeted PGD usually does. and it will give us a broader space of the manifold for the new adversarial classes. This is the complete algorithm of DBAT. It's a very standard adversarial training algorithm. We have, again, two main changes. One is to generate the adversarial example with targeted PGD when we exclude the classes that we try to attack. And the second change is to save the adversarial examples with their specific adversarial class label. Okay, so at inference time, the model will output the probability vector V, which is twice the size of the original probability vector. Remember that the original probability vector was of size C. So the final prediction will be taken as the class with the maximum probability. But what happens if the maximum probability class is an adversarial class? So we just return the standard counterpart. For example, if you got an adversarial cat label, so we will return a cat. We have other methods that doesn't take only the maximum. You can check out our paper for another evaluation. So okay, some examples. Let's start with synthetic data. So we wanted to see in our eyes how it will look like if we will apply our method to any kind of data. So we started with two isotropic Gaussian blobs. The decision boundary is at 0. In figure B, you will see what will happen if we try to apply standard adversarial training. The separator will be some complex line between the two classes. And if we apply DBAT on figure C, you can see that the lines are much smoother and easy to interpret it. So this one is for the synthetic data sets. Okay. Some more visualization. So we wanted to see in our eyes how the adversarial class and natural classes look like. So we visualize DBAT using 2D TSNE on CIFAR10. On the top left, you can see the natural classes. On the top right, you can see the adversarial classes. On the top bottom, you can see both classes mixed together. And on the right down, you can see the adversarial and natural classes painted in two colors, where the blue color is the natural class and the orange color is the adversarial class. You can see the strong separation between the classes. You can see that the natural classes almost doesn't mix, not with each other and not with the adversarial classes. The interesting thing to see that we saw here is that the adversarial classes usually mix between one another much more often than the natural classes does. Okay, some additional results. We tested the DBAT against white box PGD, auto attack, and feature adversaries on CIFAR 100, CIFAR 10, and ACE-VHN. Just a reminder, we don't try to beat the state of the art in robustness. We try to gain as much as we can natural accuracy while still achieving compatible and non-neglectable robustness to the models. So you can see on CIFAR 10, CIFAR 100, and ACE-VHN, we all got extremely high results, much higher than the other state-of-the-art and most common approaches. For example, for CIFAR 100, we got improvement of 18.5% compared to the second best approach. In CIFAR 10, we got up to 10% improvement, and in ACE-VHN, we got up to 7% improvement. We also wanted to see what will happen if someone will try to attack our model without, bypassing our projection function that narrows down the 2C vector into a C, and just try to attack the feature vector or the inner layer. So we also applied feature adversaries. None of them managed to attack the model and degrade the robustness of the model. Some more results on the natural corruption. So this corruption benchmark dataset consists of 18 diverse corruption types. It involves noise, blur, weather, and digital categories. We tested it against CIFAR 10C and CIFAR 100C. We saw very significant improvement across the board compared to some of the most common used method in adversarial training, up to 25% in CIFAR 100C and up to 25% improvement in CIFAR 10C. Some more results. Okay, so robustness to unforeseen attacks that the model did not see during the training process. So we tested the model against L1 PGD L2 PGD, L2 deep full, L infinity deep full, and CW infinity. For all attack approaches except for CW, we gained an improvement and consistent improvement against some of the most common approaches for adversarial training. On L1 PGD, we get up to 20% improvement, L2 PGD up to 14% improvement, and so on. So our method consistently improves the results even on unseen adversaries. We have a lot more experiments in the paper, but here I wanted to show the final experiment that we did. It's mainly regarding the question that I asked myself during the research: can other methods reach D-batch natural accuracy by shifting the trade-off between the natural and robust trade-off? Meaning, for example, if another method will wage the loss between the adversarial and clean losses, can they reach the natural accuracy that we reach with significant robust accuracy? So for the most suitable method to do this is trades, because trade basically does this. They wage the loss between the natural and adversarial examples. In the x-axis, you can see the natural accuracy, and in the y-axis, you can see the robust accuracy. And the most important thing to see here is that trade was not able to match D-bat's clean accuracy without losing robust accuracy almost entirely, meaning that when you try to take other methods and tune them to reach high natural accuracy, they almost completely fail and they lose their all robust accuracy. This is another empirical evidence of the unique ability of D-bat to learn models with optimal or near optimal robust natural accuracy and significant level of robustness. That's all. If you look closely, there is a QR code for the GitHub repo. So thank you, and if you have any question, I will have to answer it.